All right, moving into our final section for Domain 3, Security Engineering, we're going to talk about the implementation and operation of facility security, kind of an extension of what we talked about in the previous section. Cable plant. We need to make sure that we have appropriate documentation. Physical layer, which we'll talk about in Domain 4. We'll talk about the OSI model and what the physical layer represents, but it is the lowest layer of our open systems interconnect model. And quite frankly, if the physical layer is not secure, then it's not really going to matter what we do at any other layer in the OSI model. If we don't have any physical connectivity, we're not going to be able to communicate no matter how secure or how robust the systems we've installed are. So physical layer is the foundation of any network. Physical layer can include traditional networking components like twisted pair Ethernet and fiber optic cables, but it can also include connectivity that's not related to the network, power systems and so on. 70% of the network is composed of passive devices, cables, connectors, cross connects, patch panels, punch downs, etc. And we have to keep those things into consideration as well. Our physical medium, our copper, our coax, which really is technically copper anyway, copper cable meaning twisted pair Ethernet, coax, optical fiber, even the radios and the transceivers that we use for wireless transmission would be considered, at least the antennas are considered as a physical layer medium. The physical layer defines specifics of implementing a particular transmission medium. Are we going to use twisted pair Ethernet? Are we going to use shielded twisted pair or unshielded twisted pair? Are we going to use plenum rated cable versus non-plenum rated cable? What category rating are we going to use, which determines the frequency that particular cable operates at? What types of terminations? Am I going to have RJ45 connectors for twisted pair Ethernet or ST or SC connectors for fiber optic cable? The physical layer is relatively static, meaning that once it's installed, it really doesn't change that much. The exception would be new build-outs and expanding build-outs and so on. But for the most part, the physical layer stays in place. Some of the key components to this physical layer are the entrance facility, what we call the MPOE, the equipment room, any type of backbone cabling that we have running through the enterprise, the pathway that supports that backbone. In the case of most modern construction, that's just a fiber optic backbone that interconnects buildings or different locations within the enterprise. Telecommunications room, our horizontal distribution system. Oftentimes these systems are installed in buildings with multiple floors, so we have to be able to interconnect the different floors. So we might have fiber riser cables or copper riser cables that allow us to interconnect those different floors. What is the entrance facility? Every building has one. The entrance facility is where all of the public utilities and services come in. And of course leave the building. So your T1s, your PRIs, your voice circuits, your data circuits, they come in through some sort of entry point, whether it's through the roof or through some hole in the wall or through some underground piping or whatever, and it goes into the facility and it's going to house all of your services. And then that's what allows us to essentially interconnect this facility of this building to internet service providers or telecommunication service providers, the power company, or whoever else we're receiving services from. So it generally will have some sort of electrical protection. There'll be a grounding component to it, and then there will be what we call a demarcation point. A demarcation point is a way for us to identify where the service provider's responsibility ends and where the consumer's responsibility begins. It could be a wall biscuit. No, that's not a cookie attached to the wall. A wall biscuit is like a a place where you can interconnect or cross-connect cables. It could be an NIU, which is a test unit for digital circuits like T1s or PRIs. It could be a 110 punch-down block for traditional PSTN connectivity, or a 66. Most likely that would be a 66 punch-down block for traditional telephony. Well, it depends. It depends on the installation period, right? There's some twist, I forget what they're called, twist lock punch downs or something like that. Those are really, really old. But in any event, there's typically kind of like this panel on the wall, and that's where all of our services get installed. So you see on the left there some laser optimized fiber. Most likely that black box, you see the blue cable coming out of there, is a probably a 50 micron laser optimized fiber connection that goes to a different building. We have some biscuits here, most likely just for cross-connecting some networking equipment, or they could be biscuits for connecting voice circuits or whatnot, traditional voice circuits. These are the NIUs that I was referring to, little 110 punch-down blocks to cross-connect the various circuit paths, physical circuit paths. These little boxes here are test cards, right? Physical layer test cards that allow the service provider to loop a circuit so they can do loopback testing to verify functionality. And then the T1s come out of there. And then they go into these respective 110 punch down blocks, which then we can punch down these this cable to it so that we can cross connect or interconnect our devices. Here's another kind of similar punch down unit, kind of old school. But all kinds of things can be attached to these MPOs, right? These minimum point of entries and equipment room. The idea is that that's where the service providers bring in their equipment, and then that's where you can now connect to that equipment and utilize those services. Inside the building or inside the facility, we have our backbone distribution system that provides connectivity between the entrance facilities, our equipment rooms, telecommunications rooms, and so on. In a multi-floor building, distribution systems can be composed of different cabling. We might have something called an MDF. That's typically going to be in my primary data center. MDF is where most of your important and critical data center components, your core switches, your core routers, and so on would exist. Most of your connectivity occurs in the MDF, the main data frame. And then throughout the facility, you might have these things called intermediary data frames, because we have limitations on how far twisted Ethernet can go, 100 meters, and maybe the distance between this MDF and this IDF is 500 meters or something like that. So there'll be some sort of fiber connection between them. This could be like a little cabinet on the wall that has devices installed in it, or it could be a separate room with a rack, a telco rack, or a 4-post rack, or whatever. There's all kinds of different variations of construction. But the main data frame is typically where most of your primary equipment goes, and then the intermediate data frames are an extension of that main data frame.
With the clouding services nowadays, would you say this has changed, or is it still the same concept?
It's still the same concept, because you have to understand that we're talking about physical connectivity within the building, right? Cloud services, yes, they're not housed within the building, but you still have to have a computer to be able to access those resources. And those computers still have to be connected to some sort of physical architecture. So yes, maybe you don't have as much in your main data frame because you don't have servers in-house, and you outsource a lot of that functionality to cloud-based services, but you still have the same general architecture. You still have that same structure, because there has to be you still have to have access to the services, to the distribution services. The cloud, I always tell people that the cloud is just computing on somebody else's computer, but you still have to be able to compute to that. You still have to be able to connect to that. So you will still see this even in environments. Maybe the footprint isn't as large, but you would still see it in a campus environment. All right, the telco room or the telecommunications room, which we actually, I was going to say this is probably just your MDF, but actually it's pretty common that the MPOE, that minimum point of entry, where you have your traditional telecommunications terminations, isn't always in the MDF. It might be some closet next to the perimeter of the building, and then you extend the equipment in that telecommunications room to your MDF by using cross connects and patch panels and so on. But there are cases where it is combined with your main data frame, where you have your racks and everything else. But telecommunications room by definition is just an area where we have that equipment. Your horizontal distribution system is your typical kind of network cabling distribution system. So let's say, for example, I've got an IDF, and that IDF has a couple of switches and whatnot. Well, inside of that IDF, most likely, I have something called a patch panel. And that patch panel has ports on the front, and it has cables that go out the back. The ports on the front are what lets me connect to my switching equipment. And then the cables on the back are my home runs, typically twisted pair Ethernet cable that go to the different offices and cubicles and whatnot. Usually they're going to go to some sort of keystone jack on the back. That keystone jack is just like a little plug where you can punch down the cable, and then it has an RJ45 connection, and you can plug your PC into that. And that comprises that horizontal distribution system, at least for end user connectivity. There's other types of communication systems horizontally, like fiber optic connections to interconnect your IDFs and MDFs and so on. But the idea is that we're just providing a structured pathway for the data to flow. The most common elements that we see in any cable distribution system would be the cabling itself, the various connectors. Maybe you might have some media converters thrown in there as well to convert from copper to fiber or whatnot. Some repeaters if runs are too long. Patch panels, which allow us to create an interface to interchange how the connections occur to our switching equipment or our networking equipment. Keystone jacks, antennas that are placed around the facility if you have wireless environments in place, fiber optic connections. You might have fiber splice trays where you have all your fiber going to these different pigtails that go into the fiber patch panel. There's all kinds of components that include your cabling distribution system. Whether it's horizontal or vertical, it doesn't really matter. I've been doing networking for, at least physical plant networking for 30 years. I think I started doing physical plant in when did I start? Probably 1993 or 94, around that time frame, when I was dealing with things like 10 base 2 and 10 base 5, thick net and thin net, and vampire taps and AUI connectors and so on. So it goes way back, even prior to twisted pair Ethernet. And now we have all kinds of options for distribution systems today. A server room, by definition, is exactly what it sounds like. We have servers housed in racks, and depending on the robustness of that room will depend on what types of equipment you might install in that room. If you have high value assets in that room, of course, the first thing is to protect access to that room, physical access. So you'll have biometric security. You might have static protection mechanisms, anti-static devices placed throughout the room, static ESD, electrostatic discharge straps and stuff. You'd have biometric security to get access to the facility. And then inside the facility, you might have rows of racks. They could be cabinets. You have all kinds of different ways of racking equipment as well. Open rack systems versus closed rack systems. It just depends on the environment that you're installing it in. A telco rack is just kind of a 2-post rack, 19-inch rack, and you got your rails here that you can attach equipment to. It's a completely open system. You have 4-post racks if you have server rails that you need to install servers, and then you can get really fancy by installing, fully enclosed, ventilated and cooled cabinets that have their own individual security. I mean, we did some training and some consulting for American Express, and we were doing some training at one of their facilities, one of their data center facilities, which happened to be the largest one in the country. And the systems that they had in place were amazing. These racks were all liquid cooled. They had cold water inlets and hot water outlets for every rack. And we're not talking about just 20 or 30 racks. It was the room was literally the primary data center floor was probably, and I'm not even exaggerating, probably 3 football field lengths. It was that big. So we were talking about hundreds and hundreds of cabinets with servers just churning away. They had their own power plant. I think for that particular facility, they had 12 or 15 12-cylinder diesel engines for generators. They had their own local power substation. It was pretty crazy. This can scale to a very large environment. It can be relatively small, but you're kind of still generally using the same technology. Now, the rack system that you decide to use for your server rooms will depend on, what type of servers you have in place. Just some considerations. We used to have, I used to own a service provider organization. So we would do dial-up and T1s and whatnot for customers back in the day when that stuff was popular. And rather than having our own physical facility, we hosted all of our stuff at a data center, at a commercial data center that we paid for rack space in. And their racks looked something like this. They were not that wide, but they were standard 19-inch racks. But they were fully enclosed racks with doors, securable doors on the front. But the doors had like these slats. And that was the ventilation component that they had for these cabinets, was they had slats in them that were probably maybe an inch wide or maybe an inch and a half or 2 inches wide to allow for airflow through the cabinet and so on. And one of our neighbors had some equipment in their rack, a switch or something like that, and it had a bunch of these SFP modules in this device, a small form factor pluggable module, which is just a module that allows us to connect copper or fiber or whatever. And somebody went in and pulled all those SFPs out because they could get through the slats to get access to them. And those things are like gold. They sell them online or whatever. So different considerations. You wouldn't expect something like that to happen, but sure enough, it did. So server room security needs to be reviewed. That's the whole point of the last bullet point. Consider as many options as you can, but there's likely other options that you haven't even considered. Yeah, you want CCTV. Yes, you want multi-factor authentication to access the facility, and so on. All right. Rack security. It's unusual for everyone to need access to every rack. So the rack locks or rack access control mechanisms should ensure only the correct people have access. We do tend to focus on manual access in a lot of cases for these types of environments. We don't want to rely too much on technology because ultimately the technology might fail. Like, adding biometric locks for the cabinet sounds like an interesting thing to do. But what happens when those biometric locks don't have power or they fail? So oftentimes the simplest method, which is just a key, to gain access, would be prudent because you have other mechanisms for ensuring, multi-factor authentication or whatnot to access the facility. When it comes to racks, it's important also to understand, power requirements, temperature requirements. You often will install what we call hot and cold aisles. So you've got your HVAC system, your heating, ventilation, and air conditioning system, and you have your racks in the data center, and you have what are called hot and cold aisles. So this might be a hot aisle, this might be a cold aisle, this might be a hot aisle, this might be a cold aisle. So the equipment, the airflow would be something like this, right? Where you have the, this is a cold aisle. So the airflow is taking the cold air, moving it. Most servers use horizontal cooling mechanisms, not vertical cooling mechanisms. So the air flows through the server because we stack them in the rack. So you've got your cold air, and then that cold air is being heated up as it goes through the equipment, and it gets evacuated into the hot aisle. So you've got your cold air from your HVAC system blowing down into the cold aisle, and then you got your air being evacuated from the hot aisles in the air return vents and stuff like that. These are all kinds of things that you need to consider as you're designing these systems and implementing these systems. All right. Restricted access. One of the things that if you're involved with the federal government is this sensitive compartmental or compartmented information facility, what we call a SCIF. Typically associated with the military, right? National security or defense. They can be permanent or they can be temporary, but it's a highly restricted work area where maybe top secret or secret information is discussed, national defense security, or other types of information. There are very specific requirements for building these SCIFs, whether they're portable or whether they're permanent. Access to the SCIF typically is going to be limited to individuals that need access. They have to have the appropriate clearance to gain access. Non-cleared personnel might be allowed if they have constant oversight or if the SCIF is not presently being used to discuss classified information or classified material is removed from the facility. And then there would be other restrictions like mobile devices are not going to be allowed, recording devices. We might even include noise generators and stuff like that to block out eminence or to remove emanations, from leaving the SCIF and so on. The SCIF can be located in a vehicle, if it's temporary. But there are some directives that we follow to ensure that these SCIFs are protected. The Director of Central Intelligence Directives, DCIDs, specifically 1/21 and 6/9, and then the Intelligence Community Directive 705, based on signed by the Director of National Intelligence, identifies a document that identifies how these SCIFs are supposed to be constructed. Not only that, computers that are operating within the facility also have to conform to specific rules based on Tempest. Tempest is a national security, an NSA specification. It's been around for quite some time. That talks about information systems and specifically leaking emanations, radio or electronic signals, sounds, vibrations, etc., and what we would need to do to protect against that. All right, we see some of the directives here, right? SCIF walls need to consist of 3 layers of 5/8 inch drywall, from true floor to true ceiling. Now, these were written at the time that this was created. These specifications may have changed a little bit. Typically, there's only going to be one entrance door. It's going to have some sort of X10 combination lock. Nowadays, though, I think we tend to use kind of more modern locking mechanisms. The X10 is a pretty well-known locking system, but now we'll have things like biometric keypads and whatnot that we'll use as well. All right. These are the directives that I was referring to. Directive 1/21, DCID, Director of Central Intelligence, Directive 1/21. The SCIF perimeter doors have to be plumbed in the frames, and the frames need to be firmly affixed to the surrounding wall. The door frames have to have sufficient strength to preclude distortion that could cause improper alignment of the door alarm sensors, improper door closure, degradation of audio security. The SCIF's primary entrance doors need to be equipped with an automatic door closer. The HVAC system with any duct penetration into the SCIF has to be secured in anything that's over 96 square inches, including man bars. We maybe should call those person bars nowadays, to prevent entrance. Sound masking, I was being facetious, by the way. Sound masking placed over the doors in front of plenum or pointed towards windows to prevent listening of classified conversation. Access control must be managed from within the SCIF, and intrusion detection gets sent out to a central station, which would require an armed response within 15 minutes. Oops, what did I do there? There we go. All right. So I'm sure that these are not the only directives, but you don't need to know all of these details for the exam. I just want to give you an idea of what some of the common directives are for SCIF construction. Okay. Data center security. This can be quite an extensive conversation, right? The data center is obviously typically the heart of our IT infrastructure. So obviously data centers need to be protected. Really not any different than what we've been talking about this entire time. Make sure you have multiple layers of defense, dual control, functionality, multi-factor authentication to access the data center. Make sure you have the appropriate, hot and cold, design to manage temperature. Make sure you have the appropriate power backup systems, and so on. Because it is typically the head of our computer operations, we need to make sure that it's relatively robustly designed, right? Start with an entry into the building, passing the receptionist or guard, and then using some sort of proximity card to gain building entry. So not only are we concerned about immediate access into the data center, which would require some sort of secondary or tertiary authentication, but what about just gaining access to the building that houses the data center? So for example, when we were hosting our equipment at this data center, this commercial data center, there was a front door. We went in the front door. We would have to sign in and register at the desk, which would include presenting our ID and presenting some sort of kind of rudimentary authentication, like a PIN code or a passcode. And then they would provide us access to the data center. And if we were bringing equipment in, we would have to provide an inventory of that equipment, or if we were taking equipment out, we would have to provide an inventory of that equipment, and so on. And then you go up to the data center floor, go up the elevator, go up to the data center floor, and then you had physical access to the floor. So that would include some sort of hand geometry scanner or biometric security that you would have to, participate in. Could include a man trap as well. In our case, it didn't, but and then that would give you access to the floor. And then you would get access to the cabinets, and the cabinets themselves would have security, a physical key or some other way of accessing the cabinet. So multiple layers of defense. And then, of course, you had other mechanisms like cameras and whatnot, that a CCTV system where they could monitor the data center, look at the different rows and stuff like that, and you can also install your own security systems as well, put in your own cameras and whatnot. So that's the defense in depth approach. You have different levels. In some cases, in those floors, we had companies that had cages inside the room. So once you got into the data center floor, there was a cage because they had maybe 4 or 5 or 10 racks. So they had their own cage. So they had an additional layer of defense. But door controls, man traps, closed circuit televisions, biometric authentication, all things to consider. There's an example of a man trap, a person trap, palm vein biometrics. That's kind of a new thing. Traditionally when it came to biometrics, it was, and we'll talk a lot about biometrics later on in a different domain. Retina scan, iris scan, fingerprint scan, maybe voice recognition, hand geometry scanning. But palm vein scanning is kind of the newest thing, right? Where you're actually looking at the pattern of veins in the hand, because that requires life, whereas a fingerprint does not require life. And that, believe it or not, that pattern doesn't change over time, not significantly. And it's like a fingerprint. It's completely unique to that individual. So kind of an interesting concept. But we'll get into the biometric stuff a little bit later on. We also concern ourselves with utilities and power, loss of power. You need to have a backup power system. Batteries are okay for immediate use, and typically batteries will kick in pretty quickly. So the way most enterprise or commercial power systems work is you're running on city power, and there are some power conditioners and power monitors to monitor city power. And if that power goes below a certain level, or it becomes, or it disappears altogether, or it becomes kind of dirty, I guess, like a brownout or something like that, the battery packs will kick in. Now, those battery packs are probably not going to last very long, depending on how many batteries you have and how well they're maintained, but the battery packs will kick in, usually just to maintain power. And then there'll be some logic in the power system, the backup power system, where you have this automatic transfer switch. And this automatic transfer switch will intelligently start the generators. Once the generators come up to power, they'll usually let the generators run for a few minutes to make sure they're not going to fail. And then they'll automatically switch the power over from battery to the generators. And then the generators typically will run consistently depending on how much the fuel cells hold and so on. Of course, you want to make sure those generators are functional. We would often go out when I was working at NASA. Of course, we had generators everywhere and backup power systems everywhere. And we would test those power systems every month. We would run the generators every month. There's liquids inside of those generators. I mean, they're just basically truck engines, right? Diesel truck engines. If something sits stagnant for a long time, it gets gummed up or, it doesn't work. So we run the generators every once in a while. And even test the switchover systems, the intelligence, and so on. So that's something to consider. UPS. UPSs are useful for power conditioning. They kind of provide circuit protection for spikes in voltage or fluctuations in voltage and amperage. But they also provide power if city power or the commercial power is not available. The batteries guarantee continuous operation, but batteries have a lifetime. It's interesting that I mentioned that because the latest thing that I discovered, right, that I did not know existed. The school for this carnival had asked, I have a couple of generators at home for various reasons, one for my house and RVs and camping and stuff like that. And the school had asked to borrow those generators for the carnival. And so I pulled one out. I hadn't run it in a while. I had to clean out the carburetor, do some things to get it working. But the battery was not charging. It was just a kind of a liquid cell battery. It wasn't a dry cell battery. So it just wasn't working anymore. So I went to get a new battery. And the guy, I said, look, I want a battery that I don't have to maintain and that will last a long time. And he said, he grabbed a battery off the shelf. It's one of those little small, not like a car battery, but one of those little small batteries that you might see in like a Power Wheels or something. And he threw it at me, and I'm like, And he said, here, check this out. And he threw this battery at me, and I caught it, and I was like, what is this? This is a display unit or something. It weighed practically nothing. And he said, well, that's lithium ion. Yeah, they're starting to make batteries now that are lithium ion for those types of applications. I know that's not probably that surprising, but I had never seen it before. I thought it was pretty cool. Because one of the issues that we have with UPSs is the consumables on those UPSs. Batteries lose their ability to store charge over time. A battery that might be effective today for 3 or 4 hours of runtime in a year might only be effective for about 20 or 30 minutes of runtime. So something to consider, right? But we know what a UPS is. I think everybody listening to this probably understands the need for a UPS and the value for a UPS. We will typically purchase and size UPSs to give us somewhat of a minimal amount of runtime. They're not intended to provide power for long periods of time. They're intended to provide power until either the city power is restored or the brownout goes away or whatever, or until some generator kicks in. So that is but it's called an uninterruptible power supply because it kicks in immediately and hopefully you don't lose power to your facility. Generators, we know what those are. They typically run on diesel fuel because they're usually truck engines, but smaller generators run on standard fuel, like the one you might have at home or something like that. But you want to make sure the generator is protected. As long as that generator has fuel, it should run. And most generators or most facilities have more than one generator, and they'll test them on a regular basis. But they need to be protected. So here's a pretty diagram of what a commercial data center might look like. You've got your racks, you've got your airflow, intelligent airflow system where you got your hot and cold aisles. You've got your air conditioning unit, and then you have your power distribution modules, which have your intelligent switching systems, to go from battery power to generator power. You got a generator, your generator transfer switch, which usually will operate automatically. The one I have at my house is manual, but your UPS, maintenance bypass, where you can actually switch to alternate power sources if you're trying to implement some sort of maintenance and so on. So these are the kinds of things that you might see. All right. HVAC, heating, ventilation, and air conditioning, also a consideration. Heat can cause a lot of damage, so you want to have cooling options. And they define two different types of cooling features here. Latent cooling, which is the ability of the air conditioning system to remove moisture, typically for comfort cooling applications like office buildings, retail environments, and so on. So we're maintaining this balance of temperature and humidity, which surprisingly enough, humans need. We need humidity. And sensible cooling. basically just removing heat. Data centers will typically use sensible cooling as opposed to latent cooling. So you might see some reference to those definitions on the exam. Fire suppression systems. This is something that you will most likely need to know, at least in general. There are 4 different groups of fire systems: wet, dry, pre-action, and deluge. A wet system is a constant supply of water. Once it's activated, it will not turn off until you shut off the water source. A dry system does not have any water in it. A valve will not release until the electric valve is stimulated by some event, which in this case would be a some sort of fire, right? So we would have some sort of valve that reacts to heat. It could react to other things as well, but heat is pretty typical. A pre-action system incorporates detection systems that can eliminate concerns of water damage because of false activations. The water is held back until the detectors in the area are activated. And you could have multiple detectors. And in order for that system, that pre-action to be triggered, multiple events would have to occur. Deluge systems operate the same as a pre-action system, except every sprinkler head is in the open position. So as soon as the water starts running, it's going to go into every system. Water is okay for things like warehouses and whatnot, but as you can imagine, it's somewhat inappropriate for electrical equipment and computer rooms. So we have other fire suppression systems that we use in other types of environments. Aero K is an aerosol of microscopic potassium compounds in a carrier gas. They're canisters mounted on the wall. We don't see these anymore, but I remember seeing these before. The generators to release the gas are not energized or pressurized until a fire is detected. And then we have multiple fire detectors that have to be triggered before the fire is confirmed. The gas is non-corrosive. It doesn't damage metals or other materials, and it doesn't harm electronic devices, and it is non-toxic. But there is an issue with Aero K. It sucks the oxygen out of the room, so to speak. So you don't want to be in a facility where this stuff is being discharged. FM200, another type of gas. There's a big long name to describe it. Heptafluoro, I don't know what it is. Heptafluoropropane? I don't know what the actual name is. That might not be correct. But so it's a colorless, liquefied compressed gas. It's stored as a liquid, and then it gets dispensed as a colorless, electrically non-conductive, clear vapor. All right. It leaves no residue, and it has acceptable toxicity, whatever that might be. It does not displace oxygen, so that's why it would probably be used over Aero K. So you can still occupy the space even though it has been dispersed throughout the space. So that's it. We are done with domain number 3. All right, let's move on to domain 4.